We've mentioned carboxylic acids an awful lot in this course thus far, not just in the organic sections, but also when we were talking about acids and bases. So it's kind of like we've got this old friend here about whom we know absolutely really nothing. So hopefully in this module you'll learn a little bit more about that old friend carboxylic acids. Carboxylic acid group is a carbon double bonded to an oxygen, so it's that carbonyl group that we see in aldehydes and ketones, but also bonded to this OH. Okay, if you've got the carbon without the OH, it's an aldehyde or a ketone. The carbon with the double bond has to then also go to an OH to be an acid. If we think about what the general formula of these will be, we've got a double bond in there to a carbon, so of course that reduces the number of hydrogens by 2. We have another oxygen that does absolutely nothing for us in terms of the general structure, so we have 1 degree of unsaturation with that double bond, and so CnH2nO2. We name them using the suffix ethanoic acid. So the simplest carboxylic acid, with which R is H, so there's just the one carbon in there that's part of the group. Sometimes students forget about the carbon that's part of the group, so it's a 1 carbon acid, methanoic acid. Now, more than any other group of organic compounds, acids are referred to so much by their trivial names. So again, it's important that you recognize those. So methanoic acid is what you find on A-level papers. Talk to a practicing chemist, and it's formic acid. Next one, of course, is where R is a methyl group. This would be ethanoic acid, so 2 carbons. A lot more people use ethanoic acid than methanoic acid, but even so, the vast majority of chemists would call this acetic acid. Put in an ethyl group instead of the methyl group, and you can see how I'm actually leading into the confusion of forgetting about the carbon that's in there. There's 3 carbons in this. It's a prop, but one thinks about it as the acid group plus an ethyl group a lot of times to give you those 3 carbons. So propanoic acid, the proper name, the extremely different propionic acid as the trivial name. Interestingly, I believe, although I haven't fully fact-checked it, that the prop as the prefix for 3 didn't come from propane, it came from the old name of propionic acid. So I said, oh, 3 carbons, let's use prop for 3. See that similar thing when you have a 4 carbon carboxylic acid, a butanoic acid. The older name is butyric acid. So again, you can see this but came from the but led to the but, not the other way round. And then 5th one here, pentanoic acid, is often known as valeric acid. Something to note here about acids is they smell in an idiosyncratic fashion. I don't particularly mind the smell of acetic acid. However, everybody in the world minds the smell of butyric acid. I used to do a lab years ago in which I had students smell various organic compounds, and you had pretty things like vanillin, which obviously smells like vanilla, and a cinnamaldehyde, which obviously smells like cinnamon. And then we had butyric acid, which smells like disgusting, dirty, sweaty, cheesy, moldy feet. And after a year of doing this lab, once a term, my boss came and he said, could you find something else to illustrate a nasty smell? Because as soon as you open up the lid, within 5 seconds the entire lab smells like a disgusting locker room. But anyway, acids smell bad. Continuing on, you can have dicarboxylic acid. So this one here, in which it's a prop, you've got 3 carbons, 1 from this acid group, 1 from this acid group, and then 1 bridging in the middle. This is the second simplest dicarboxylic acid. The simplest is one that you will actually see if you haven't seen it before in the coordination chemistry, oxalate, where you just have 2 carboxylic acid groups essentially bonded together. But anyway, propandioic acid, often known as malonic acid. Malonic acid leads to compounds that are extremely important for certain organic syntheses that you'll see when you get into probably the 2nd year of university studies. Few other ones to throw at you. There is benzene carboxylic acid is its proper name. Benzoic acid, much easier name to say. If you've got a double bond in there, propenoic acid, and the carboxylic acid group takes naming priority. So if this was one where there would be an issue with it, this would be carbon 1, and then the alkene would just be numbered wherever it happened to be. And you can see that this priority even takes place for an alcohol. So here we've got, this is a 1, 2, 3, so propanoic acid at the end. The alcohol is at carbon number 2. Some other funny names: acrylic acid you might often see when you're dealing with polymers, because acrylate, which comes from acrylic acid, very important polymer, and lactic acid is the old-fashioned name for the 2-hydroxypropanoic acid. Physical properties, well, here's our usual list that we keep adding to. When you have just the hydrocarbons, all that they have is dispersion forces, and so they have low boiling points. Go up to the carbonyl compounds, propanol and acetone, that have dipole-dipole, so they have higher boiling points. And of course, propanol can hydrogen bond, so it has a really high boiling point. If we take the carboxylic acid that has about this same molar mass, ethanoic acid or acetic acid, you can see it has an even higher boiling point. Ethanoic acid can also indulge in hydrogen bonding, as can all carboxylic acids. What's particularly cute about carboxylic acids, though, is they have 2 hydrogen bonding positions. This carbon-oxygen double bond can act as a hydrogen bond acceptor. It doesn't have its own hydrogen that it can use, but it's sufficiently negative that it will accept the hydrogen from another hydrogen bonding donor. But we also have a hydrogen bonding donor in the carboxylic acid with this oxygen here. So as well as hydrogen bonding all over the place, carboxylic acids will dimerize in solution with these 2 hydrogen bonds. So the second one here, the donor OH group, can hydrogen bond with the carbon oxygen double bond acceptor of this, and its OH donor can therefore return the favor, going back to the carbon oxygen double bond here. So this dimerization of carboxylic acids, very important to realize it can do it. It contributes to the higher boiling point because alcohols can't really dimerize like this. But it also led to some interesting other observations that you can see if you go to the colligative properties aspect of the solutions module.